emocional, mas não vou por conta sombra. Vou viver a minha vida da sombra, na fonte dos tu casa. Te dá alegria, não dá.
Assalamualaikum and hi to Dr. Nurajmi. So my name is Ahmad Mukri Hakim bin Muhammad Shukri. Matric number CN 240157. So I want to explain for this lab for P control. So this lab we just study for PID tuning for fluid level control system using Labview simulation. So for this time I just set for the KC for the KC set for the 10. So we can see that the tank level is increased very slowly. So and the process variable PV stop below than the set point, and then the last steady state error is exists, and the graph show smooth but low final value. Why this happen for this KC10? Because the proportional control response depend only on current error, and then with a small KC the controller output is weak, and when the error becomes small the valve stop opening further, and then the inflow equal outflow before reaching the set point. If you can see for the 100 KC, the graph show the faster rise time compared to KC10, and then the steady state error is smaller. Output is very fast to disturbance, and then the system still do not exactly reach 100%. Yes. Why this happen? Because the higher KC multiply the error more aggressively. The valve open wide for same error, and then we go through for the last set point for the KC is the 1000, and then for the 100 we can see the graph show the very aggressive response, overshoot and instability more appear. And then why this happen? Because controller react strongly even to small error, and then the system approach stability limit. So for the conclusion for the 1000 KC, we can see the fast but risky for the operation controller. So the conclusion for the P only, not include the I and D for the PID tuning flow, we can conclude that the result will going the fast but not accurate.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ibn Afiq bin Abdul Rahman, and my matric number is CN240018. And now I would like to show my part. And my part is PID, but I use my part is PI. It's using PI only. First, we need to insert the value. My KC value is 10 and my TI value is 5. Here 5, and our set point is 80. Here, right first. Yeah. As you can see in the process chart, the process variable, when the process variable reach the set point, it takes so much time. It takes so longer time. Just like in this slide, as I can show you the result here. observe me first. Okay. The settling time it takes 8,587 seconds to reach the steady state error. To reach the process variable to reach the set point around this time. This is because it takes much longer because the integral action is sweet and slow, and the controller takes a very long time to eliminate the error. Okay, then we set the value for 0.5. 0.5 here. Stop this and run it. Okay, for this part, for the second part, the process variable takes a little bit less than the first one because the integral action becomes stronger and settling time improves, but the error is not fully eliminated. But it is still slow for this type of system, but much better than TI value 5. The process variable take a little less time to reach the set point, as you can see here. And the settling time for this 0.5 is 847 seconds. The rising time is only 18.97, and the steady state error is 4.93. And then for the third part, we only change the TI value for 0.0 0.005. Yeah, just like this. Right? 0.05. Sorry. Now, try to bring it. And as you can see, it takes a little bit less. It takes a shorter time between the TI5 and TI0.5. And as you can see here, yeah, it is very fast. The process variable reached the set point at the low time, and my time that I recorded it is 162 seconds, and the rising time is 39.39 seconds, and the steady state error is only -0.25. This is because the graph shows faster rise and quick settling reach the set point accurate with oscillation. And the 0.05 is much better than the 0.5 and 5 TI. Okay, that's all from me. Thank you.
Hello, Assalamualaikum. My name is Muhammad Azari bin Muhammad Yusof. Matrix number CN240054. So today I want to make a presentation about PID. So my part is PID. As you can see, first experiment is we make KC10 TI 0.05 and then the TD is 10. So for this lab, I need to find steady state error, then settling time, and also rise time. For steady state error is how to find steady state error. So how to find the steady state error is set point minus PV value. For settling time, which is we need to get the value about 2% plus minus or 5% plus minus of value PV, which is process variable. For rise time, how to get the value rise time is we need to get the 10% of the value set point, then 90% value for set point, and then the last we minus the value 90% set point minus with 10% value set point. So we get the value rest time. So this is the maximum value that I get, which is 0.66. As you can see, the value of PV cannot reach the set point value. This is because the PID with large TD reduces controller output too much and too early, causing the inflow to be insufficient. Even at 100 output, the inflow cannot overcome the leak, so the system stabilizes below set point value. Okay, next I want to calculate the steady state error from the value of process variable. So how to calculate the steady state error? The formula is set point minus with steady state error. So I get the result is 16.34 because 80 minus with 60.66. Next, for settling time. So how to calculate the settling time? We need to find 2% plus minus from the PV value, which is 60.66. So the value is 58. So if we look at the graph, the 58 process variable, then we get the settling time is 588 seconds. Okay, the last is rest time value. Actually, for calculate the rest time value, the formula is we need to look at the set point value, but in this case, the process variable cannot reach at the set point value. So I just take the maximum process variable value, which is 60.66. So we find the value for process variable, which is first 10% and also 90%. Then we minus the value 90% with 10%. So we get the rest time value is 355 seconds. Next, the second experiment is we just change the value of TD with 1. So the final value is 60.06. Then we calculate for value steady state error, which is set point minus with process variable value. Then I get the steady state error is 19.94 value. Then we need to calculate for the settling time.
for settling time, I take 2% minus from the value process variable, which is 58. So the settling time is 619 seconds. Then for the rest time, we need to take 10% and also 90%. So the value 90% minus with value 10%, then I get the value is 355 seconds. In the value rest time, we need to take off the value set point, but in this case the process variable cannot reach at the set point value, same as like TD in time value. So I just take the value in maximum process variable. Then the last one, we need to change the value of TD with 0.01. So we get the value of process variable, which is the value is stable on 80.06. Then we calculate the steady state error value, set point minus with process variable value, then we get negative 0.06. Then we calculate the settling time, which is I take 2% minus from the process variable value, which is 78, and the value of 78 reach at settling time 219 seconds. Now we calculate the value of rest time. So how to calculate the value of rest time? We take 10% of the value process variable, which is 8, and also 90% value of the process variable, which is 72. So we minus value 72 with 8, then we get 171 seconds. So as you can see at the value, why the value of process variable on the third experiment can reach to the set point value. This is because the TD value is small. It's like doesn't have the value of TD. So the process variable can reach to the set point without any disturbing, because the TD is derivative. So if doesn't have any derivative, the graph doesn't have any disturbing, and the process variable will reach to the set point with clearly. So for the conclusion, the more small value of TD, the more clearly graph you will get without any disturbing. That's all from me. Thank you.